So in this video, I'm going to show you how we can use properties of similar triangles to actually answer questions about the world around us, some application problems. For example, how could we go outside and tell how tall a tree is? If you had a really long, I don't know, bunch of yardsticks or a long tape measure, maybe you could climb to the top of the tree and see how tall it is. But there is a much easier way to do it, and it's actually to measure your shadow. So we may do this in class, we'll see if we have time. But what you would do is you could go outside and measure your shadow. And so let's pretend that you're standing like right here. There you are. Or that could be me, that's fine. Notice that the tree shadow is kind of coming this way. And so I'm guessing the sun is somewhere over here in this picture. And so here's the tree shadow, and here's your shadow. Okay, so let's say you've got a tape measure, and you measure your shadow, or you have a friend measure your shadow, and your shadow is 4.5 feet. And your height is, you are 5'7" and a half, because, you know, gotta be specific here, 5'7" and a half. Okay, you also measure the tree's shadow. So the tree's shadow is, let's say it keeps going for a ways. You would have to use a tape measure and actually measure it out, but the tree's shadow, let's say just for this problem, is 56 feet, which is a lot longer than your shadow, and that makes sense. And using this information, I can find the height of the tree. Because what I have just created, basically your shadow and your height forms a similar triangle to the tree's shadow and the tree's height. So first of all, how do I know that these are similar triangles? I know this because of the angle-angle property, or postulate. The first pair of angles that I know is congruent would be this right angle that forms the tree and the ground, and this right angle formed with you standing and the ground. So those are both congruent. And then I also know that this angle and this angle are congruent. The reason for that is because of the sun. The sun is beaming down at the same, basically in the same way to both the tree and to you, and so this angle is the same because of like the sun's rays. So I know these are similar triangles, which means I know that all the sides are proportional, which means that I could set up some ratios with my height and my shadow and the tree's height and the tree's shadow. So here is, let's pretend that's you, not me. You have a height, so let's make this your height and your shadow. Your height was 5'7" and a half. First of all, let's convert that to feet. 7.5 inches out of 12 inches for 1 foot is 0.625. So basically I just converted this into just pure feet, so it's 5.625 feet. Okay, so that's your height, 5.625 feet. And compare that to your shadow, which was 4.5 feet. Whatever that ratio is, it should be the same as the tree. So the tree's height to the tree's shadow. We don't know the tree's height yet. I'll just leave an X there because that's what I'm trying to solve for. The tree's shadow, though, we measured, it was 56 feet. And now you can cross multiply and solve for X. So do 56 times this. So 56 times 5.625 should equal 4.5 times X. So multiply by this, divide by 4.5, and you should get 70. So 70 feet is the height of the tree. And if you want to check your work, make sure that it worked, do like this divided by this and make sure it's the same decimals, 70 divided by 56. You could have also set this up different ways. You could have done 4.5 over 56 equals 5.625 over x. That would work too, like shadow to shadow equals height to height. That would work as well. Let's try another one. Oh, another way you could do this, if you don't have somebody to help you measure like your height and your shadow, one way that I've seen people do this out in the woods is put a stick in the ground. Like say I put a stick here that's like 1 foot tall, and I could measure the stick's shadow. So let's do this. Let's say the shadow was 0.8 of a foot. So let's line this one up a different way. Let's do like the tree's shadow was still 56 feet, and we still don't know the height of the tree. Maybe just pretend this time. So I could do like shadow to shadow, so 0.8 to 56 should be the same as stick to really big stick, 1 to x. And again, if you cross multiply and solve for x, you should get 70. 56 times 1 divided by 8 is 70 feet. Divided by 0.8, sorry. Here's one more example. How can we tell if a basketball hoop is 10 feet? On this one, you could probably just reach your yardstick up or reach like a tape measure up and see if it's 10 feet. But if you can't reach that high, you could do what we just did, which is measure its shadow and measure your shadow and see. I don't know why I didn't give you arms, sorry. So I'm going to give you some sample measurements here. So imagine that the shadow of the basketball hoop is 5 feet 3 inches. Imagine that the shadow of the person is 2 feet 6 inches. And I assume we're going with that same height from last time, so 5.625 feet. That would be your height if you're 5'7" and a half like I am. Okay, so we don't know yet if this is 10 feet. So the height of the basketball hoop is like x. It's basically like we're trying to solve for that. So again, these are similar triangles. Like this right here, this triangle is a similar triangle to, I don't really know where I guess we're going with this height here. It's a similar triangle because these are the same because the sun, and these are the same because they're right angles. And so by angle, these are similar triangles. And so I can set up a proportion of this to this is the same as your height to the basketball's height. Or you could do like this to this is the same as this to this. Let's go ahead and convert these to feet real quick. 3 inches is 1/4 of a foot. So like 5 1/4 or 5.25 feet. And 6 inches is 1/2 of a foot. So this would be 2.5 feet. So I know that 2.5 was my shadow and 5.25 was the basketball shadow. That should compare with my height, which was 5.625 feet, and the basketball's height, which is just unknown at the moment. Hopefully it's about 10. So when you cross multiply, let's see what we get. So I'll do 5.25 times 5.625, which is 29.53125 equals this times x. So now divide by 2.5 and see what you get. I got 11.8125 feet. So it seems like the basketball hoop is 10 feet, which is a pretty standard hoop for like high school, I would assume. Except for, this one has one little twist, which is we measured the shadow of the basketball hoop, which is probably caused by the top of the backboard rather than the hoop itself. So this height that I just found is probably all the way up to the backboard, and I want to know about the hoop. So how do I go from 11.8 approximately down to where the hoop is? And so I'll give you a little information. On a standard basketball hoop, this is typically 2 feet. So knowing that information, if I take 2 away, I'm at 9.8 feet. So is it 10 feet? The answer is actually no, but it's very, very close. Just needs 0.2 of a foot.